Okay, hi everyone. So, commuting operators is the last section of this chapter. So, what are commuting operators? So, if we have an operator on V and another operator on V, then we say they commute if TS equals ST. Now, what does this mean? This is an equation of operators. So, how do we show two operators are equal? We're not showing, but I'm just trying to understand what this means. It means that TS is like doing T after doing S to a vector of V. So in other words, TS is another operator on V, and TS applied to a little v should be equal to ST applied to a little v, where ST is another operator on V. So once you have two operators, you can compose them, do one after the other, and that gives you more operators, and then you're saying that these two ways that maybe look different would be the same. Oh, they won't be the same for most operators. So in other words, T and S commute if ST equals TS. In other words, STV equals TSV for all vectors. Okay, these two operators have to do the same thing to every vector. Okay, so that's what it means. The book writes blah, 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 blah for an arbitrary polynomial in two variables, x and y, of degree less than or equal to m. Explicitly write out this sum for m equals 1, m equals 2, m equals 3. Okay, so this is just getting a handle on this notation here, which looks pretty ridiculous. But let's set m equals 1. Now, j and k are powers, and they have to be integers because we're talking about polynomials here. So you can't do like x to the half. I mean, of course, you can do the square root function, but we're not going to do that because we're just doing polynomial functions. These are sort of the simplest ones. So these j and k can be 0 or 1 or 2 or 3, etc. But if they're less than or equal to 1, then the only way to do that is either j equals 1, k equals 0, or j equals 0, k equals 1. So for m equals 1, this sum here has only two terms. Oh, wait. There's the third term. J equals 0, k equals 0. Because that is still 0 is less than or equal to 1. In other words, this sum has three terms. It would be the a00, x0, y0 term, the a10, x1, y0 term, and the a01, x0, y1 term. In other words, this is a polynomial a00 plus a10x plus a01y. And this is really what it is. It's a sum of three terms. The degree is bounded by 1, so we can have a constant term and we can have linear terms in the variables x and y. That's really how to think about this. All of this stuff is just decoding precisely this stuff up here and this stuff up here is for a computer. For a human, we think about that the case for m equals 1 is degree less than or equal to 1. That means I can have a constant term, an x, and a y term. And I'm just naming these coefficients, which are numbers like 3, 4, 5, pi, 17, 1/2, according to the convention AJK. All right. Now let's go up to, if we keep going up to 2, of course we have all the terms we had before, but now we can have more terms because we're allowed to go up to 2. So I'm going to get my constant term, my linear in x, my linear in y. Now my quadratic in x. Now my mixed quadratic term, 1 x and 1 y together, and then my quadratic in y. And this is now the sum for m equals 2. Okay, so this is now this is an arbitrary degree 2 polynomial in two variables. And for m equals 3, I can have the 3, 0, x to the third, the 2, 1, x squared y, the 1, 2, xy squared, and the So that's a degree 3. You see I have 4, 3, 2, 1. Does that continue? If we went up to degree 4, yeah, there would be 5 terms in degree 4, corresponding to x to the 4th, x to the 3rd y, x squared y squared, x y to the 3rd, and y to the 4th. Okay. Are commuting matrices common or rare? They are rare. For physics majors, what is true of commuting operators in quantum mechanics is not true for operators that do not commute. Okay, so commuting operators in quantum mechanics are special. Of course, they're special because of the linear algebra that we're going to prove down here. Okay, that they have simultaneous diagonalizability. But in quantum mechanics, what does that mean physically? It means that, so if two operators commute, so commuting operators correspond to observables that can be measured precisely, like can be known, you can know the value of these observables. So what's an observable? Okay, what's an observable? By the way, this is not a course in physics, but energy, you might measure the energy, you might measure the position of something, you might measure the momentum of something. So these are all observables. And in particular, position and momentum are related by this famous Heisenberg uncertainty principle, that you cannot, the more precisely you know the position of a particle, the less you can know about its momentum. The more you know about its momentum, the less you know about its position. And there's a fundamental relation. I can't remember exactly what it is, but this has to do with the fact that position and momentum correspond to operators that do not commute. Okay, they do not commute. But if you have two operators that commute, then it's possible to know both. If position and momentum commuted, then it would be possible to know the position of a particle exactly and know the momentum of the particle exactly. But that does not happen in quantum mechanics, and hence the idea that particles travel along trajectories, through space is no longer true. Okay, so the next thing we will do is we will precisely prove a theorem about eigenspaces and commuting operators. Okay, what is that theorem? So when operators commute, then blah blah blah, you can measure them simultaneously in physics. But what about math? And that math will be the reason behind the physics. But the key is that an eigenspace of one of the operators will be invariant under the other. So like the lambda eigenspace of T will be invariant under S. And vice versa, the lambda eigenspace of S will be invariant under T. And, it doesn't matter what we call each operator. If Ts equals St, if T and S commute, then each eigenspace is invariant under the other operator. So let's prove this. How do we prove? So let V be in the lambda eigenspace of T. Okay, then Tv equals lambda V, right? We need to show that this space is invariant under S. So when we do S to V, we need to show that it's still in the eigenspace. We need to show that SV is in the lambda eigenspace. Well, so that means we need to show that, when is it true that that a vector is in the lambda eigenspace? Well, when we apply T to that vector, we should get lambda times that vector. So is this true? Well, let's apply T to the vector V, and then let's use the fact that these operators commute. But V was in the eigenspace, so TV is lambda V. And then S is an operator, it's linear, so we can pull the lambda through. And that's exactly, and then we just put parentheses, and that's it. So we took something in the eigenspace, And to show it's invariant under S, that means S times it has to be in the eigenspace. But to be in the eigenspace means we need to hit it with T and show that we get a lambda. And we do. End of proof. Prove that diagonalizable operators are simultaneously diagonalizable if and only if they commute. Okay. So let's assume, so if and only if means we need two proofs. So first this proof, say TS simultaneously diagonalizable. Okay, what does that mean to be simultaneously diagonalizable? There is a basis v1 through vn of v with both m of t and m of s diagonal matrices. In other words, this basis consists of eigenvectors of t, and these are also eigenvectors of s. And so, m of t might look like lambda 1, lambda 2, lambda 3, and m of s might look like mu 1, mu 2, mu 3. This is mu, it's a Greek letter, mu. Just what we typically call another eigenvalue, lambda and mu, if there's a second one. So, we need to show that they commute, right? We're assuming that they're simultaneously diagonalizable, and we need to show they commute. Well, TS is equal to ST exactly when the matrix of TS is equal to the matrix of ST. Because, this M that eats an operator and spits out its matrix is an isomorphism. And also it's even more than that. It respects the multiplication. So M of TS is just M of T matrix multiply M of S. And this is M of S matrix multiply M of T. And so we're just we have the matrices. And you know how you multiply these matrices together? You just get lambda 1 mu 1, lambda 2 mu 2, lambda 3 mu 3. And then that's exactly the same thing as if you first wrote the mu matrix and then multiplied it by the lambda matrix. Everything else is zeros. I hope you know. So we proved that, therefore we proved that. So that's it. If they're simultaneously diagonalizable, there's a basis where they're both diagonal matrices, but diagonal matrices can be multiplied in any order because these numbers can be multiplied in any order. Lambda times mu is mu times lambda for any complex number or real number. Okay, so then what's the other way? So now the other way is, let's say they commute. We need to show that they're simultaneously diagonalizable. Okay, so they commute. Oh, well, if they commute, then their eigenspaces are invariant. So say TS equals ST, then E of lambda T is invariant under S. Right? So I can choose, and S is diagonalizable. Okay, we're talking about diagonalizable operators here, so it's a sort of a special case of operators. And if they commute, we need to show that they're simultaneously diagonalizable. Okay, just because two operators commute doesn't mean that they're diagonalizable. We're just saying, look, if you have two diagonalizable operators and they commute, then they should be simultaneously diagonalizable. Okay, so the lambda eigenspace is invariant under S. So choose a basis. So, S is diagonalizable, but that means S restricted to any subspace is diagonalizable. Okay, so that means that there's a basis of eigenvectors here. So choose U1 through UL, a basis of eigenvectors of S, and they're basis of what? Of what space? Of E lambda T. Okay, but then these vectors here are a basis of E lambda T. That means they're all eigenvectors. Okay, so these vectors are eigenvectors of S, of T too. Therefore, they're eigenvectors of T too. Okay. Now, T is diagonalizable, so the whole space V can be written as a sum of all the eigenspaces, a direct sum of all the eigenspaces. And so now we've just shown that on each space there is a basis that's eigenvectors, that's simultaneously eigenvectors of T and eigenvectors of S. So you just, because this is a direct sum, you just string together the basis on each of these spaces that we know exists that respects S, because each eigenspace is invariant under S, so we can choose a basis of eigenvectors of S. And then within here, now we've got eigenvectors of S, eigenvectors of S, eigenvectors of S in our bases. But those are coming from each of these spaces, so they're eigenvectors of T too. And that means that our operators are simultaneously diagonalizable. There's a basis of eigenvectors that are eigenvectors for S and for T, and we use the invariance of the eigenspace. Okay. Prove that every pair of commuting operators on a complex space has a common eigenvector. Right, so commuting operators don't have to be diagonalizable, but what we're showing here is they do have to have at least that first common eigenvector. Well, first of all, let's say we have T and S. Well, they're each operators on a complex finite dimensional space. So T has an eigenvector, has an eigenvalue and eigenvector. Let's call it V, with TV equals lambda V, and V is non-zero. So we know that from before, that on a complex finite dimensional space, every operator has an eigenvalue and eigenvector. Okay, but then that means that the lambda eigenspace of T is non-empty. Okay, but then it's invariant under S. Right? S takes this back to itself. So then S restricted to this thing is an operator on a complex finite dimensional space. This is a subspace, so it's definitely finite dimensional. And so this is an operator on a complex finite dimensional space. It has an eigenvector. There exists a W such that SW equals mu W. Right? And so there we go. And W is in this lambda eigenspace. So W is your answer. Okay, and again, we use the invariance of the lambda eigenspace of T under the commuting operator S. Okay. So there is a theorem in this section about commuting operators being simultaneously upper triangularizable. And this is a harder theorem. The proof of this is harder. So because I just want to point out first the meaning. Remember, commuting operators, if and only if they're simultaneously diagonalizable, but we're assuming that those operators are diagonalizable each. But not every operator is diagonalizable. So this is a little bit stronger. It's saying, look, no matter the operators, if they're commuting, then they're simultaneously upper triangularizable. Okay. Now we know that commuting operators are always upper, or we know that any operator on a complex space is upper triangularizable, right? So this is on a real space. Not every operator is upper triangularizable. So I think this theorem is going to require the complex numbers, and the proof is a bit hard. So I want you to read this theorem and see if you can understand it. The idea is that we know that we can at least get a first common eigenvector, right? So choosing that common, I guess I called it W, eigenvector, and then extending to a basis of the whole space will allow us to sort of write our space as the span of W, direct sum, something else. I think your book calls it capital W, which is a little bad because I called this little w. But I think your book calls this little d, so let's just do that. And what you're going to show is that sort of this decomposition will allow us to use induction on the dimension. So this space right here will have one less dimension. On a one-dimensional space, everything is upper triangularizable, right? Because you have a 1-by-1 matrix. There's no lower diagonal entries to even worry about being non-zero. But now we're going to do induction, and this space will be our smaller dimensional space, and we'll be able to assume it's true here if we can show that the commuting operators still commute on this space. And in order to do that, we'll get something called a projection operator. We'll take the big space and we'll project down to V. So once we show that our whole space can be written as a direct sum of this subspace and this subspace, then any vector in the whole space can be written as, something in here, so some little AV plus some W, where little w is now in here. And the projection operator just forgets this factor. Okay? Just project. So in your mind, you should maybe think about if we had a vector somewhere in three-dimensional space, like this vector here, then its projection might be, we just forget the upward component and we project down. And so capital W would be like the xy plane here. And we just forget the z component, like the amount of movement in the upward direction is just forgotten, and we project. Okay, so this will really come up in chapter 6, and already we see a hint of it here in the last section of chapter 5, that projection operators are very useful. Anytime you have a space and you can write it as a direct sum of subspaces, you can immediately define a projection operator onto either space, where you just take a vector here, and because your space is a direct sum, there's a unique way to write V as something in the first subspace plus something in the second, and this is unique. And so you can just define it, so if you want to go to U, you just forget the W piece. U such that V is equal to U plus W is the unique way to write blah, 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 blah. Okay. Now in chapter 6, we're going to do something even more special called orthogonal projection. And that's where this direct sum is actually sort of like a 90 degrees kind of thing. But we're going to need a way to measure the angle between vectors. So we're going to need a sort of dot product, or it's also called an inner product. And that's the subject of chapter 6. Okay. But projection can be used even without an inner product, as long as you have a splitting of your space as a direct sum. That means you can write any vector uniquely as a piece in each space, and projection just forgets one of the pieces and keeps the other piece. So that's sort of the idea of this proof, and it's an induction on dimension, and you have to use a projection operator to sort of make sure that the commuting operators still commute. Okay. So let's look at this last question. If ST and F are commuting operators on a complex space, what do we know about the eigenvalues and eigenvectors? Or no, just the eigenvalues, I guess. So because it's complex and they're commuting, we know that they're simultaneously upper triangularizable, but we know the eigenvalues of upper triangular matrices are just the entries on the diagonal. So what's going to happen here is that we choose the matrix of S and the matrix of T, so that they're under a basis that gives them simultaneously upper triangularizable. And then when you multiply these matrices, the diagonal entries of the sum, when you multiply them, the diagonal entries will just be the multiplication. So, let me just show you an example. 1, 2, 3, 3, 4, 5. So if I multiply these out, what I'm going to get is 3, 0, 4, 15. And what you see is that this 3 is just 1 times 3. This 15 is just 3 times 5. And so because we can simultaneously upper triangularize our matrices, then when you multiply the operators, the eigenvalues will just multiply on the diagonal, just because of how matrix multiplication works. So this is one of the advantages of knowing the nice matrix forms exist, is you can immediately show that the eigenvalues of ST are just multiplications of the eigenvalues of S times the eigenvalues of T. Let's see. And if you add them, the eigenvalues will add. Now, let's say we get the eigenvalues. I mean, the order might matter here. So all we really know is that the eigenvalues of ST are among the possible products in eigenvalue of S times an eigenvalue of T. I think that's right. Let's just double check that to make sure. Yeah, so this is a kind of a weak statement. Every eigenvalue of ST is some eigenvalue of S times some eigenvalue of T. That doesn't mean that every possible product appears, but they definitely are of that form. Okay. So that's it for that section. Next up, inner product spaces, and angles and distances and cosines and data science and least squares. That'll be fun.